Welcome back, everyone, to another explainer. So, if you're an aspiring cloud engineer or honestly just someone who wants to understand the invisible plumbing that makes the entire modern internet function, you are in exactly the right place. Today, we're setting our sights on a fundamental piece of the OSI model, the network layer. We're going to unpack exactly how data packets navigate the absolute chaos of global networks to arrive safely at their destinations. Let's get into it.
Okay, here's our roadmap for today. We'll start with the network layer's job, then we'll dive inside the data plane, followed by inside the control plane, and finally, we'll wrap up with a collaborative network operation.
Section 1. The network layer's job, the ultimate director. Right, so before we can understand the specific parts, we really need to understand the whole.
The crucial point here is that in the OSI model, the network layer is basically the ultimate director. Its absolute main responsibility is routing packets between entirely different networks. Think about it. Without this layer, your data would just sit locally. It would be completely unable to find its way across the vast, super complex web of interconnected devices that we call the internet or the cloud.
And to actually pull off this massive routing job, the network layer splits its functions into two very distinct areas. On one hand, we have the data plane. This is the doer, right? The muscle. It's responsible for the actual physical movement of data packets. And on the other hand, we have the control plane. This is the thinker, the brain of the operation, entirely responsible for making the routing decisions. So one handles the strategy and the other executes the move.
Moving on to Section 2. Inside the data plane, fast active execution. We're going to speed things up a bit right here, mostly because the data plane doesn't pause to ponder, it just acts.
So, the data plane's primary job is forwarding. It takes packets from a source and aggressively moves them toward a destination. To pull this off, it relies heavily on info contained right inside the packet headers, specifically the destination IP address. It also references routing tables, which are basically just maps, to determine the absolute best path based on metrics like the shortest route or link quality. It just reads the map and sends the packet on its way. Boom. Now that actual movement of data packets from one network device to another, that's called packet switching. And the data plane accomplishes this using a few distinct techniques. It might use store and forward to meticulously check for errors before sending the data along, or maybe cut through for immediate high-speed delivery the absolute second it reads the destination. Or it could use virtual circuit switching to establish a dedicated pre-planned path. These are the literal mechanisms the data plane uses to physically push the data down the line.
But wait, how does it actually know what device is which? Well, that brings us to logical addressing. The network layer assigns logical addresses, which we all know as IP addresses, to uniquely identify every single device on a network. I really want to highlight this. Without these unique logical IP addresses, proper routing by the data plane would be completely impossible. It would be exactly like trying to deliver mail to a house with no address on a street with no name. It's just not going to happen.
All right, Section 3. Inside the control plane, methodology and strategy. Let's transition away from that fast-paced execution for a second and take a look at the thinker, slowing our pace just a bit to establish the actual rules of the road.
Let's see how this builds the foundation for literally everything the data plane just did. The control plane manages some massive background jobs. It manages the routing tables, meaning it actually builds, populates, and updates the maps that the data plane relies on. It computes the best paths using some pretty complex routing algorithms, and it handles error recovery by detecting network failures and triggering reroutes. It's essentially the brilliant tactician sitting in the war room, making absolutely sure the network operates efficiently.
And to build those accurate tables, devices in the network actually have to communicate with one another to exchange information about routes and network topology. They do this using specific routing protocols like OSPF, BGP, and RIP. You can kind of think of BGP as the massive protocol that runs the global internet, while OSPF handles localized internal networks. These protocols are basically the shared languages that network devices use to whisper to each other, constantly updating the control plane about what the network environment looks like at any given millisecond.
The control plane also handles some highly specialized management tasks. On one side, we have traffic engineering. This is all about making decisions to optimize network performance and resource utilization, basically ensuring your bandwidth availability is used to its absolute maximum potential. On the other side, we have quality of service, or QoS. QoS sets policies to ensure that highly critical traffic, like say a live video call, gets preferential treatment over less critical data, like an email just sitting in your outbox.
Section 4. A collaborative network operation, working in harmony. We've met the thinker and we've met the doer, but an efficient, reliable network operation requires both of them to work in absolute harmony. So let's bring them together.
Now, what's really interesting about this relationship is how directly these two planes depend on each other. While the control plane is busy building the tables, computing the best paths, and detecting errors, the data plane takes that exact logic to use the tables, execute the forwarding, and physically move the data. The data plane is entirely, 100% dependent on the rules and the logic that the control plane creates. Without it, it's just flying blind.
This quote directly from our source material perfectly summarizes our key takeaway for this explainer. The data plane is concerned with the actual movement, while the control plane is responsible for making decisions about how that movement should occur. They're two distinct halves of the OSI network layer, but they must work intimately together to ensure efficient, reliable network operation. You simply cannot have a functioning modern network without both of them doing their jobs.
Which leaves us with a critical and, honestly, a slightly provocative thought to end on. If the control plane, the thinker, the table builder, the error handler, goes down, how long can the data plane keep moving packets based on the last set of rules it received before total chaos ensues? It's a fascinating question about network fragility and just how absolutely necessary their ongoing collaboration really is. Think about that as you continue your cloud engineering journey. Thanks for joining me on this explainer, everyone, and keep questioning how it all works.